So, good afternoon. Let us continue our lectures on commutative algebra and algebraic geometry. So, last lecture we have seen definition of a K algebra and when is it finitely generated, etc., etc. And one of the prime example we study in this course is the polynomial algebra over arbitrary commutative ring, and even in that case we will fix base ring to either to a field or to ring of integers, and then it will give us some analogues in algebraic geometry as well as algebraic number theory. So, that is one of the reason that I am spending more time on the basics of commutative algebra. I still need little bit more, but let us see how we can go to geometry and combine algebra with geometry. All right. So, in the last lecture what we have done is, for any commutative base ring, this is a ring, base ring, we have defined what is an A algebra. Also we have defined when do you say it is finite type over A. Finite type over A. This is same thing as, also sometimes people use it, finitely generated A algebra. Finitely generated A algebra. And the typical example of a algebra of a finite type over a commutative ring is, so this is typical example. Typical examples are polynomial ring over A in finitely many indeterminates x1 to xn, and also the quotients of this x1 to xn modulo an ideal A, where A is an ideal in the polynomial ring. So, these are the typical examples. So, therefore, we have to study these rings little bit more for example, what happens ideals there or prime ideals or maximal ideals and so on. And mostly in the beginning I will take mostly our base ring, we will take A equal to a field or we will take A equal to Z, ring of integers. Okay. So, first of all we should say, so I want to also clarify what is the difference between finitely generated algebra and finitely generated module, because what is roughly A algebra is what? A algebra by definition I will write a ring, commutative ring which is also A module, where the plus here equal to plus here and the scalar multiplication of this and the multiplication of this ring, they are compatible with each other. So, that is an algebra. Now, first of all, what should be a homomorphism between algebras? So, let us define that. So definition. So, A as usual, A is fixed base ring, let B and C B2 A algebras. A map from F from B to C is called an A algebra homomorphism when it respects the algebra structure. If so, what, how many conditions? So, first of all, one, F should be ring homomorphism. So, again I want to remind here, under ring homomorphism we are assuming that identity element, multiplicative identity goes to multiplicative identity. That is very important. Okay. Second, F is an A modulo homomorphism. And what is an A modulo homomorphism? It is additive. So, that is additive, that means it respects the addition, but the addition is here also. So, it is this additivity is checked here also, and K linear, and so and respect the scalar multiplication. So, K linear I would say, together it is called K linear, not K, A linear. A linear. That is an algebra homomorphism. But if I think it is better to write in a different way for, so algebra I will think now, I will not think ring and module and compatibility, that is all built in the saying that B phi is an algebra, right, where phi is a structure homomorphism, that is from A to B. And similarly C psi, these are the two algebras given to A to C. So, when do you say map is a algebra homomorphism? F from B to C is an A algebra homomorphism if this diagram B, C, this is given F and A here, and there is a structure homomorphism here phi, there is a structure homomorphism here, that is psi. If this diagram is commutative, that simply means if I go this way, same thing as this. So, psi equal to F compose phi, that means the diagram is commutative. So, this is much simpler to abbreviate it, and it is equivalent to that one, that you can check easily. Okay, so that is algebra homomorphism. So, as usual, the collection of A algebras I will denote by ALG, and homomorphisms of one K algebra from one K algebra to the other K algebra is denoted by that set, is denoted by hom K, not K, A ALG from B to C. That is, these are the set of all A algebra homomorphism from the A algebra B to A algebra C, and with this collection it will form a category of A algebras. This again I will come back, right now just this collection and this, and what is the obvious thing that we will need is composition of two algebra homomorphisms. Algebra homomorphism identity map is an algebra homomorphism, and so on. Okay, and we will keep adding more. Right now, identity and identity B, and if I have F from B to C and G from C to D, if these are A algebra homomorphisms, then G compose F is also an algebra homomorphism. That usually you check it for every groups, rings, and so on. All right. So, now at least I want to describe all A algebra homomorphism. Say the typical algebra I want to consider is A x1 to xn. This is my one A algebra, and the other algebra is B, let us say. So, this is A algebra. So, if you want, you can think B phi, and I want to describe all A algebra homomorphisms from this polynomial algebra, and that is the reason why it is called polynomial algebra. So, polynomial algebra. Polynomial algebra over A. These also keep, because the elements are polynomials. Okay, now how do you construct? So, let me give first one example, and then we will see how to write more general. So, example, let us take A equal to Z and only one variable n equal to 1. So, my A algebra is Ax, Zx. So, that is Zx, polynomial algebra over Z in one variable, and B I am taking it Q. This is my B, and I want to write algebra, some algebra homomorphism. So, let us take any rational number x, small x, fix any rational number. Then there exists a unique Z algebra homomorphism from Zx to Q. I will denote this by epsilon x, which maps x to x. So, this is obvious, because all that we have to check is this is a ring homomorphism and this also is a Z linear, right. These are the two things we have to check. But well, where will x square go? If you want it algebra homomorphism, x square I have no choice, it has to go to wherever x goes, x time, wherever x goes times that. So, this has to go to x times x, small x square. Similarly, all powers will go to the powers of that small x, and it should be Z linear. So, if I want somebody like this, A x cube plus B x5, then first of all it is additive. So, this will individually I can make, and A has to go to A, and because it is Z linear. So, this term will have to go to A x cube and this addition plus B x5. So, therefore, this map is uniquely determined. This map is in fact any polynomial capital F, Fx, this will go to F evaluated at x. This one is precisely, if this is Fx, this is precisely F, capital F evaluated at x. Only wherever you find x, you write small x. So, that is why this map is evaluation map. This is evaluation at x. So, you could take x equal to half, x equal to 5/6 and so on. So, and all algebra homomorphisms has to be like this, because x has to go somewhere and that you call it small x, and then everybody is uniquely determined. So, this is called a universal property of this polynomial algebra. Okay, so we will abbreviate I will formally record it. This is a proposition. This is very important. It is used very often and mostly it is not said what we are using it, but this is what is being used always. So, this is called universal property of polynomial algebras. Very important. So, let A be our general A be our ring and B is an A algebra and B1 to Bn, they are elements in B, they are given elements in B, they are given. Then there exist a unique A algebra homomorphism from the polynomial algebra over A in n variables to B. So, these I will denote with the same explanation epsilon B, where B is this tuple B1 to Bn. What is the map? Xi should go to Bi for every I 1 to n, and then this is uniquely determined, because where will a arbitrary polynomial will go? If we demand this, then the arbitrary polynomial have to go to f and substitute for xi's bi's, f of b1 etc bn. So, substitution, this is also called a substitution homomorphism, substitution homomorphism, or also some people call it evaluation homomorphism, evaluation map, because we are evaluating at B1 to Bn, and the proof does not need anything, because it is an algebra, you want an algebra homomorphism. So, it should respect addition, it should respect k-linearity, and also it should respect multiplication in the ring. So, that determines where the polynomial goes. Okay, so, proof, I will just say easy verification, and you should individually you should do yourself homomorphism. So, what does this mean? Let me spell out what is it in algebra homomorphism means. I want to spell out clearly. So, that means what? That means if I want to write, see, remember in the above notation epsilon b of f is not this small f, I should use capital F. F equal to f of b, where b is the tuple b1 to bn. So, we have substituted. So, what does it mean by ring homomorphism? So, first of all, epsilon b of f plus g, capital G, this should be, on one hand it should be f plus g evaluated at b, but this also should be, so this should be, because it is a ring homomorphism, it should be epsilon b evaluated at f, I mean image of f under epsilon b plus epsilon b evaluated at image of g, but this is same as epsilon evaluation f capital F b plus capital G at b. So, this should be equal. So, that means this evaluating or substituting b is additive. Another one is similarly by the same explanation, epsilon b of f times g equal to f of b times g of b. These are, on other hand, it is, I should write that first. So, this is f g evaluated at b, this should be same as f b g b. This is very important, both these rules are very important for evaluation of polynomials. Okay. So, and what does the above proposition describes? It describes the set of all A algebra homomorphism that we have denoted like this, hom ALG A x1 to xn comma b. This set we have explained, we have described completely, and to describe any homomorphism you need only a tuple of n tuple of elements from B. So, that means what? That means that is B power n, other set is B power n, this is B cross B cross B n times, n times. And what did we do? We gave a map from where to where? We gave a map from here to here, namely tuple B, which is B1 to Bn, which goes to epsilon b, substitution homomorphism by B. So, we gave this map, and uniqueness gives this map is injective, and surjective is also obvious, because given any algebra homomorphism, that is uniquely determined by the values of x1, x2, xn. So, that I call it B1, B2, Bn. So, this map is actually isomorphism. This is an isomorphism, bijective. There is no structure, I am only saying the map is bijective. So, when time comes, we can identify these two sets. Okay. And there is nothing special about this finite n. So, let me write for arbitrary number of indeterminates. So, that is hom A algebras from the polynomial ring now in many variables indexed by I, xi, I in I, this 2 sum algebra B, A algebra B, and where can I take it now here? B power I, B power I. And what is B power I? Think of B power I as maps from I to B. These are maps from I to B. So, each map will give you a tuple and each tuple will give you a map. So, either you can think of Bi, I in I, or think it is a map from which map? From I to B, I going to Bi. Given any map from I to B, you can get a tuple, and given any tuple, you can get a map. And better to think this way, maps. Okay. So, these two sets are bijective. All right. So, that is it. Now, I want to also, okay, next observation I want to make. So, I want to use these observations to give you some examples of maximal ideals, for example, in a polynomial ring. That is 2 lectures back we were discussing maximal ideals and we wanted to give more examples. So, how do we give more examples is this. I will use this observation. So, this is examples. So, now I will take my base ring to be a field, K is a field, and I want to give maximal ideals. So, we would like to give explicit examples of maximal ideals, where ideals in the polynomial ring. All right. So, I fix, I am going to, as you have noticed, these k power n tuples. These are, let me write them A equal to A1 to An, and we have given a map from home A algebras, K algebras from the polynomial ring to where? In K. So, remember back of your mind that K equal to B in the above notation. And what is the bijection? Any element A, where does it go? It goes to epsilon A. Epsilon A is a algebra homomorphism from Kx1 to Xn to K, where Xi's are mapped to Ai's. That was the map. Right. So, given this A, we have this epsilon A. Epsilon A is a algebra homomorphism, this is K algebra homomorphism, and it is obviously surjective. Is it surjective? Is it clear? Because 1 has to go to 1, once you know 1 has to go to 1, and it is K linear because it is a K algebras. So, this epsilon A is surjective map. For every A in K, A in K power n. All right, we know it is surjective. So, what is the kernel? Let us compute the kernel. So, kernel of this, I want to check what are the generators for the kernel, this ideal. This is an ideal in the polynomial ring. So, this one I will list some elements which are obviously in the kernel. So, for example, x1 minus a1, this polynomial, this is free from all other variables. This is obviously in the kernel, because what do I have to do to check it is in the kernel? I have to check that when I substitute xi is equal to ai, it becomes 0. So, I have to substitute x1 equal to a1. So, it is 0, and remaining variables we do not have to, they do not appear, so nothing happens. Similarly, x2 minus a2 and so on. So, xn minus an, all these linear polynomials, they are in this kernel, and therefore, the ideal generated by these polynomials, it is the smallest ideal which contain these polynomials, but these are also here, therefore, this inclusion is obvious. So, kernel contains this ideal generated by this, and this kernel, because it is an algebra homomorphism, 1 has to go to 1. So, 1 cannot be in the kernel, Therefore, this cannot be unit ideal. Therefore, this is a proper ideal of the polynomial algebra. And I want to prove now it is equal here. I want to prove this is equal. This is equal I want to prove. So, let us prove that. So, what do we have to prove? Every polynomial in the kernel is written as a combination of x1 minus a1, x2 minus a2, xn minus an, and a coefficient should be in the polynomial ring, because we want it to be an ideal. So, take any polynomial in the kernel f. So, let f belong to the kernel. So, that is f of, when I substitute in f instead of variables, this small a is a1 an equal to 0, because it is in the kernel. On the other hand, this f is a function, f is a continuous function, it is a polynomial function, therefore continuous function. I am offering one proof. The pure algebra people might find it little bit more difficult, but it is obvious. So, it's a, think of it as a polynomial function, and therefore, it is a differentiable function, and therefore, if you remember Taylor's theorem, what does it say? Taylor's expansion at is, so this will be equal to what? So, I want to expand. So, what do I want to do? I want to expand. So, not equal to this. So, this I want to expand. I want to write such a formula for arbitrary polynomial. So, let me use the next page. Given any polynomial f, f of x1 to xn, and a is any given point in a k power n. This is equal to f evaluated at a1 to n plus some coefficient x minus a1, some coefficient x minus a2, and so on, plus some coefficient x minus an. You can fill up what are the coefficient, plus now somebody, now these are, I have taken one at a time. Now it will be x minus a1 square terms, and also the mixed terms, plus somebody times x1 minus x1, all this is x1, this is x2, this is xn, x1 x2 minus a2 square, and so on, plus somebody x1 minus a1, x2 minus a2, 2 at a time, and goes on like that. Now, this is a Taylor's expansion at a1 to an. So, now what are the coefficients here? This will be partial derivative of f with respect to x1 evaluated at a1. This will be partial derivative of, so let me write this. This is f suffix x1 evaluated at a1 to an. Similarly this, and this. Now, in this, if you stare at it, this term is given to be 0 for us. So, where do f belongs to? Now, you can take out this. This is in x1, x2, xn, and this you can absorb here. This you can absorb here, because x1 minus a1 you can take out, and remaining part you can absorb in the coefficient. Similarly this, similarly so on. So, therefore, it is, the equality is clear, but this proof involves this formula. But let me tell you also directly. So, we want to check what? We want to check that we want to check that if f of a1 a2 an is 0, then you have a expression like this, f equal to some g1 times x1 minus a1 plus gn xn minus an. This is what you want to prove. You can prove also directly this. So, all right, or either this or directly prove this is equivalent to proving what. So, directly prove that this ideal generated by x1 minus a1 xn minus an is a maximal ideal. In k x1 to xn, because if you prove this is a maximal ideal, this is a bigger ideal than that, this is a bigger ideal than that, and this is a proper ideal. So, there you have no chance but this. So, that would prove the claim. And how does one prove that this is a maximal ideal? How does one prove this is a maximal ideal? You go modulo it and check it is a field. But you see, we have this diagram k x1 to xn, to that k, this is the substitution homomorphism epsilon a, and then we go mod this maximal, this ideal, this is the residue map, and this is the map induced by this in when we studied the residue class ring, that is I denoted by bar. This diagram is commutative, but this map I already noted, this map is surjective. This map is surjective. Therefore, and we have gone modulo the kernel. So, one of the theorem I proved, one of the observation, one of the corollary I proved earlier, that this has to be a bijective map, this has to be an isomorphism. So, therefore, we not only get this quotient, this residue class ring is a field, but it is isomorphic to k, it is a specific field isomorphic to k. Therefore, this is maximal, and therefore, it proves that. So, we get lots of examples of maximal ideals. So, what do we get? Let me summarize. We get that all the points here, they give you maximal ideals. So, let me note that we will use it for the future. So, what we have proved? We proved that SPM of k x1 to xn this set of all maximal, these are all maximal ideals, and this k power n, and k power n we have identified with this m a, this is generated by x1 minus a1 xn minus an. We just now check that this is a maximal ideal, and as a varies in k power n. So, let me clean up little bit. Maximal ideal MA, this is x1 minus a1 xn minus an, this as a varies in k power n. This set we have identified with this k power n, and this is a subset here. That is what we proved, each one of them is maximal. So, we have ample number of maximal ideals, but this may not be equal here. I would like to be equal here, but it may not be equal. In general, we will give example, so that this is not equal in general. Okay. So, I will continue this in a later half. I will produce maximal ideal which is not of this type for some fields. Okay. So, after the break we shall meet to continue. Thank you.